My name is Ashley Copenhaver, and today I'm going to tell you all you need to know about the Higgs boson particle. First, let's split the Higgs boson into two parts, the Higgs and the boson. Now, what is a Higgs? Is it a new dance move? No, I don't think so. The Higgs actually stands for Peter Higgs, the scientist who helped discover, or actually predict, the existence of the Higgs boson in 1964. But Peter Higgs was not the only scientist trying to work on this theory. 5 other scientists in 1964, and a few others after 1964, were trying to find a way that this theoretical boson could fit into modern physics. The fundamental forces had to be connected somehow. First, let's talk about gravity. What is keeping you down on the Earth? Let's imagine that you're in a roller coaster. How are you staying in your seat, and how is the roller coaster staying on the ground? Well, that's due to gravity, because gravity pulls you to the center of the Earth. Next, let's talk about electromagnetism. This is the force that keeps the atoms of your seat pulled together and attracted to each other so that you don't fall through the seat while you're riding in the roller coaster. The strong nuclear force keeps the nucleus from falling apart. Weak nuclear forces deal with radioactive decay and more specifically beta decay, which means that in the nucleus, neutrons can be transformed into protons or electrons. Peter Higgs said, well, what about mass? How does that fit into the picture of modern physics? This led to his prediction that there simply must be some kind of mass-generating boson. So now let's take a look at the other half. What's a boson? A boson is a force-carrying particle in nature. No, it does not physically carry a force, but it does help to mediate the fundamental forces of physics. Take a minute and think about this. Alright, time's up. If you still don't get it, don't worry, we're gonna go back and review what a force is. A force is any interaction, maybe a push or a pull, that when unopposed, can change the motion of an object. This change in motion is most commonly a change in speed, so the object is either slowing down or speeding up. Now that we remember what a force is, I'm sure that we're all on the same page, right? Or maybe you have another question. I'm sure that I know what it is, though. How does force relate to mass? How did Peter Higgs make it relate to mass? Good job paying attention to the first couple minutes of my video. In order to find out the answer to that question, we're going to have to take a trip back in time to learn about Isaac Newton, that famous guy we always hear about. Isaac Newton had 3 laws of motion, but today we're only worried about one, the second law of motion. Newton's second law states that the acceleration of an object as produced by a net force is blah blah blah. None of that really matters. All you have to know is that F equals ma. That is, force equals mass times acceleration. And there you have it, the relationship between force and mass. Let's go back to the present day. So now that we know the history and what the 2 parts of the Higgs boson mean, let's combine them and find out what they mean together. The Higgs boson particle is part of the Higgs boson field that exists throughout all of outer space. This field is what gives all matter mass. Watch what happens when atoms go through the Higgs field. Watch how they interact with the Higgs boson particles. We'll observe a proton and an electron, but first the proton. See how it's moving slowly and it's bouncing off a lot with the Higgs boson particles? Now let's watch the electron. It's not interacting quite as much with the Higgs boson particles. Because we know that an electron has less mass than a proton, if an atom interacts less with the Higgs field, then it has less mass. Now let's look at the Higgs boson in relation to modern physics. First we have our fermions, quarks and leptons. We have 6 quarks, which are represented in green, and then we have 6 leptons, which are represented in orange. Then we have our bosons. They're in blue. Notice how there is still a puzzle piece missing in modern physics. We aren't quite sure what goes there, if it's just one puzzle piece or many more. CERN scientists at the LHC have found evidence that the Higgs boson particle may be this last piece. The LHC stands for the Large Hadron Collider. This is a giant ring in which particles are accelerated to extremely high speeds and then are forced to collide. These collisions produce data that is put into a computer so that the scientists at the LHC can study it. Ultimately, the scientists are trying to connect the dots and figure out what all of this data really means. There is one problem with the LHC. It only shows the reactants and products, not the transition stages, which is where the Higgs boson particle would exist. The scientists also had to use trial and error to find out what GeV the Higgs boson particle exists at. In 2012, the scientists at the Large Hadron Collider were finally able to gain enough evidence to prove that the Higgs boson particle exists. So what's next? What does it mean that the standard model has held up to scrutiny once again? Will the Higgs boson particle cause doomsday? At high energy levels, the Higgs boson particle could become unstable, and this would result in a catastrophic vacuum decay, in which the vacuum, a bubble, would increase at the speed of light. We wouldn't even see it coming, it would come so fast. But there is no need to worry. The chance of this high energy level occurring for the Higgs boson particle is slim to none. I think we'll be okay. Another theory is that Higgs boson particles decay into dark matter like black holes. What would happen if we got sucked into a black hole? Oh no, I don't want to go there now. What we do know is that we need to do more research to fully understand the Higgs boson and how it relates to physics. That's all for now. Thanks for listening.